Hi, everyone. On Friday, we learned binary search trees, which seemed like a pretty good idea, as long as they're well balanced, but they have the problem that they're not always well balanced. And when they're not well balanced, they run in linear time, and that makes them no faster than lists in the worst case. But they seem to have so much potential, because they run in log n time when things work out well. When you insert items in random order, you get a log n depth tree, and so everything runs in log n time, and that seemed like a really good place to be. We'd like to be in that place all the time, so that no matter what we insert into the tree and what order we insert things into the tree in, we wind up with a good balanced tree. Now, there's actually a whole bunch of balanced tree data structures that are taught in data structures classes. We're going to learn 2 of them this semester. Today we're going to learn 2, 3, 4 trees. Later on we're going to learn my favorites, which are called splay trees, which are the ones that I most recommend implementing in practice. But 2, 3, 4 trees it's much easier to understand why they remain well balanced. So we'll learn them first. But there's lots of other types of trees like this: AVL trees, red-black trees, B trees, many others. What they all have in common is that they have a lot of complicated updating rules for adjusting the tree to keep it balanced as you add and delete new items. So there's no way to get around complicated rules of one form or another. It's just a matter of which complicated rules you prefer. And so we'll look at one example today called 2, 3, 4 trees. And a 2, 3, 4 tree has the very nice fact that it's perfectly balanced, always, in the sense that all of the leaves are at the same depth. And so therefore, you can do find, insert, and remove operations, all in worst case log n time, where n is the number of things that you're currently storing in the tree. Now, 2, 3, 4 trees are not binary trees. They are trees in which every node has either 2, 3, or 4 children. Except, of course, the leaf nodes. But the leaves are all at the same level of the tree. Now, each node can store a certain number of entries. And the number is either 1 or 2 or 3 entries. And those are the only 3 possibilities we allow. The idea being that the number of children that a node has is the number of entries plus 1. Unless it's a leaf node, in which case it has no children. So, them's the basic facts. Let's see what one of these suckers look like. So I'm going to give you an example where this is the root node, and in this case, the root has 3 keys all stored in the same node. And since it has 3 keys, that means it has 4 children. And for this example, the children could have any number of keys themselves, but I'll keep them mostly to 1 or 2. And so this fits on the board. And then they have children. Now you can see all the one-key nodes have 2 children, just like in a binary search tree. And the 3-key node has more. Let's try to squeeze these all in here. Okay, so the 2, 3, 4 tree satisfies an invariant that's a lot like the binary search tree invariant, in that keys are placed in subtrees according to the keys in the node above. So if you look at the root node, for instance, all the keys that are less than 20 have been placed in the leftmost subtree. All the keys that are between 20 and 40 are placed in the second subtree. All the keys between 40 and 50 go here, and all the keys bigger than 40 go in the rightmost subtree. And for the 2-key node, you play the same rules. Less than 70, between 70 and 79, greater than 79, and so on. So it's the obvious generalization of a binary search tree. And just like a binary search tree, you can imagine doing an in-order traversal of this, where what you would do is you would visit everything in the leftmost subtree, then visit the 20, then visit everything in this subtree, then visit the 40, then this subtree, and then the 50, and then everything in this subtree. And if you do that, you print out all of these numbers in sorted order. So just like with a binary search tree, an in-order traversal gives you the numbers in sorted order. Now, I want to warn you in advance that I'm going to teach you algorithms for changing by 2, 3, 4 trees as you insert and remove items, but they're different than the ones in the Goodrich and Thomassia book. Goodrich and Thomassia covers this data structure, but what they do is something called bottom-up 2, 3, 4 trees. And what I'm going to cover today are called top-down 2, 3, 4 trees. Now, bottom-up 2, 3, 4 trees are a little bit easier to implement and to understand the rules for updating them. I'm going with the slightly more complicated one, and the reason why is because it's faster. It's not asymptotically faster, but it's probably faster by a factor of 2. And top-down 2, 3, 4 trees, you start at the root, you go down the tree until you find the place you're looking for, and you're done. Bottom-up 2, 3, 4 trees, you start at the root, you go down until you find the place you're looking for, then you go back up to the root again. So there's an extra pass through the nodes that makes this take a larger constant factor. And this is most important when you go to B trees, which are the main data structure used to store large databases on disks. In B trees, your nodes are actually disk blocks. So if you have to read every disk block twice instead of just once, that's going to cost you a lot more time. And that's why top-down is preferred in B trees, and so that's what I'm going to teach here as well, even though we're not going to be talking about disks in the 61B. What else do you need to know? Oh, and Goodrich and Thomassia don't even call them 2, 3, 4 trees. They call them 2, 4 trees with parentheses, and I think that naming a tree with parentheses is just too dorky for words, so no thanks. So let's look at the operations. We've got 3 operations as usual we want to deal with: find, insert, remove. So operation number 1, how do we do a find? If you understand the 2, 3, 4 search tree invariant, it should be pretty obvious. But just to confirm your suspicions, here's how it works. If I say find 74, for instance, what I'm going to do is I'm going to start at the root and I'm going to compare 74 against all of the items in the root node. And I'll see that 74 is bigger than 50, so I need to go to the rightmost tree. So I look at this node and I see that 74 is between 70 and 79. So I go visit their middle subtree. And there in the leaf, I find 74. And so I'm done. I return the entry. And a find operation doesn't change the tree as usual. So are there any questions about anything so far? All right, as usual, the tricky operations are going to be insert and remove. So as always, I'm sticking with our standard that when we insert something into the tree, what we insert is the key that we're sorting on and a related entry, which could contain all kinds of information about the key. Now, insert, like find, is going to walk down the tree. In search of the key as if we were looking for the key. But if we actually find the key, then it just keeps going because we're allowed to insert duplicate items into a 2, 3, 4 tree, just like in a binary search tree. So we'll just use the same convention we used with binary search trees, where if you insert a duplicate, you put the new k in the left subtree of the old k. And so there it goes. We proceed to k's, I'm going to call it k's left child. Now, of course, the key that contains k might contain more than one key, in which case left child is relative to k. Like if k is 50, then k's left child is this one here, not the far left child. So hopefully that's clear. The one we want to go down the subtree that's just less than 50. So that's why I put left child in quotes here. And we just keep going until we reach a leaf. So whether or not you find k, you want to keep going down the tree until you hit a leaf node. And when you reach a leaf node, you would like to put your new key there. So, if you're inserting 41, you would insert it right into this node alongside 42. The only problem with that idea is that in order to keep the running time log n, we have to put a limit on how many keys we're going to store in one node. And we've decided that that limit is 3. So once we reach the limit, if I want to add another key to a node, I have to do something. I have to restructure the tree so that there's room for a new key here. I can't just insert 61 into this node and leave it there, because then I could insert a million keys in here and we'd have a linked list again. So the big question is, how do I restructure the tree so that I never wind up with a key, with a node, that contains more than 3 keys? And to make sure that happens, we're going to use the following formula when we do an insert, and we're going to do it all the way down the tree. Whenever insert encounters a 3-key node, we are going to break it up by kicking the middle key upstairs to the next node higher. Now, you might say, how do I know that the parent node has room for an extra key? And the answer is, well, when I was coming down the tree, I treated the parent node exactly the same way. So the parent has at most 2 keys. So let's see what this looks like. Here's a portion of a tree. This may or may not be the whole tree, but if you have a portion of it like this, and you're walking down the tree doing an insert operation, and you visit this node, then the first thing you're going to do before you even think of inserting your key is you're going to restructure that node so that you don't have a 3-key node anymore. And the way you do that is the 11 moves up. And when that happens, now the top node, parent node, has an 11 and a 20. And since there are now 2 keys up here, that means it has room for 3 children now. And those 3 children are going to be 10 on the left, 12 in the middle, and the right child here is unchanged. Any questions about that? Yeah. Mm-hmm. Yep. Exactly. But when I do insert on that tree, we're going to create a new root node, and the depth is going to go up by 1. So I think I'm ready to actually do that. But before I do, are there any other questions? All right, well, let's demonstrate what we were just talking about. So suppose I do an insert 60. On this tree. Well, I start at the root node, and at the root node, I've already got a violation of the no 3-key nodes allowed on an insert policy. So the first thing I do is I restructure this top-level node, and I kick the middle key, the 40, upstairs. But there is no upstairs because it's already the root, and so that means I'm actually going to create a brand new root node with these children. So now 40 has been kicked upstairs, and that divides its compatriots, 20 and 50. They're in their own nodes now. And now I can proceed, as usual, trying to insert 60. So 60 is greater than 40, 60 is greater than 50, 60 is less than 70. I come down here, and there's another 3-keyed node. So I'm going to repeat the process, kick the middle key upstairs to make room for a new node. So the 62 moves up here. And when we kick the middle node upstairs, its compatriots get divided into 1-key nodes of their own. And the 57 goes to the left of the 62, and the 66 goes between the 62 and the 70. And now, finally, we have room to insert the 60. So 60 is less than 62, so the 60 winds up in this node. And that means, since there's only 1 key left there now, there is room to insert the 60. Any questions about that? Yes? That was the very first thing we did, because we always start at the root. We visit the root first. Every operation starts there. And as soon as we saw it was a 3-key node and we're doing an insert, we decided to kick the 40 upstairs. That's right. Well, but one thing I should say is that that does not apply to the 3-key nodes you create along the way. So one thing you'll notice is that while I was doing this process, I created a new 3-key node here that wasn't there before. But I didn't repeat the bump because I don't need to. When the bumping process only applies to nodes that were already there when I started the insert operation. If I create a new 3-key node during the insert operation, well, that won't happen on the leaf level, so I can leave this node alone until the next time I do an insert down this path. Yes? Uh-huh. if the 60 had been 50, 62? Oh, if this had been less than 60. Let's see where I started. Okay, so if you're saying if the 62 had been less than the number we're inserting, then the tree wouldn't... Oh, okay. Right, so if the number we were inserting had been, say, a 68, then we would have visited this node instead of this one, and that bumping would never have happened. I'm not sure if that answers your question. Okay. Other questions? All right. Then some reminders. I want to write down why we split the 3 key nodes that we traverse on the way down. There are 2 reasons. In the leaf nodes, it's to make room for new nodes. And in the non-leaf nodes, it's to make sure that there's room for anyone who gets kicked upstairs. And again, I want to remind you that sometimes an insertion increases the depth of the tree by 1. By creating a new root. And that's the only way that the depth of a 2, 3, 4 tree can increase. And, of course, sometimes it has to increase because the height is going to be the log of n, or at least roughly proportional to the log of n. Any more questions before the hard operation? All right. So, as always, the remove operation is going to be the trickiest one. And so remove acts a lot like entry, like find, except it removes the node instead of just returning it. So we start off by finding the key that we want to remove. And we're going to follow the same idea we used for binary search trees, which is if it's in a leaf, you remove it. And if it's not in a leaf, if it's an internal node, then we're going to replace it with the entry with the next higher key. next higher key. Now, that's the same strategy we used in a binary search tree. But one of the nice things about this here is that the next higher key is always going to be in a leaf node because of the way 2, 3, 4 trees are structured. Okay. Now we're going to have a similar problem with insert. With insert, the problem was that you might insert a node into a key and wind up with, a key into a node and wind up with 4 keys in the same node, and that's not allowed. Here we have the reverse problem, which is we might erase the last key from a node and wind up with a node with 0 keys. And having nodes with 0 keys is bad because then the tree can grow much, much bigger than n. And we don't want to allow that. So we need to make sure that when we delete a key from a leaf, that there's some other key in that same leaf. So what we're going to do is we're going to have rules for, as we walk down the tree, pulling keys down the tree so that we can always make sure that there will be a node, that there will be at least 2 keys in the leaf node that we reach in the end. So it's kind of like the reverse of the insert operation. Instead of kicking keys upstairs, we're going to pull them back downstairs, and we're going to be against 1 key nodes and try to destroy them wherever we can by turning them into 2 key or 3 key nodes. So here's the algorithm. First of all, as we walk down the tree, it eliminates 1 key nodes. And there is one exception to that rule, which is if the root only has 1 key in it, well, there's no key upstairs you can pull down. And the reason we do that is so that a key can be removed from a leaf without leaving it empty. So with the insert operation, we basically had 1 rule, but remove is a little more complicated, so we're going to have 3 rules. Rule number 1, I guess I should use a different numbering. I'll use squares. So when remove encounters a 1 key node, other than the root, on the way down, its first recourse is that it tries to steal a key from one of its siblings. It needs to be an adjacent sibling. So let me draw an example. We've got a node like this, 20, 40. It has children. One's just 10. One's just 30. And one's 50, 51, and 52. So suppose as I'm walking down through the 2, 3, 4 tree, I visit this 30 node while I'm doing a remove operation. 1 key nodes are not acceptable to the remove operation, so it's going to try to steal a key from a sibling. But the sibling has to have at least 1 extra key to give up, so you can't steal the 10 because there's only 1 key there, but we can steal the 50. However, you can't just take the 50 and put it there. because 50 is less than 40. So what we're going to do is what's called a rotation operation, where the 50 moves up and the 40 moves down here. So the 10 is the same. The node we were visiting is now a 2-key node. And the node on the right has lost 1 key. And so we're happy. We now have deleted the 1-key node that was threatening us. There's one additional thing that goes on here that you should be aware of, which is that there's also the children to consider. So here the 30 has 2 subtrees, and this 3-key node over here has 4 subtrees. Let's call this leftmost subtree S. And then there's another one here, another one here, another one here. Well, after you do this rotation operation, the middle key now has 3 subtrees, up from 2, and the rightmost key now has 3 subtrees, down from 4. What happened? Well, that subtree labeled S got moved over here. And this makes sense, because what does S represent? S is all the keys that are greater than 40 and less than 50. And in the new realm, S is still all the keys that are less than 50 and greater than 40. So this rotation works out fine. S is still in a happy place. And again, this is called a rotation. Goodrich and Thomassia call it a transfer operation. You can call it that too if you prefer. Are there any questions about that example? Yeah. The farthest node on the right? If we visited, what? The 10? Well, there's no way to get 50 straight from here over here without violating the 2, 3, 4 tree invariant. So no, we can't reach across from here to here, grab this key, and easily move it over there. Well, you could do it with 2 rotations, but that's not how we're going to do it. If the 2 neighbors, like if your adjacent siblings don't work, then we're going to have a different fallback, which is a little simpler than doing this double rotation. You could do it, though. Question? Then that's why there are 2 more steps coming up. Maybe I should go through the 2 more steps, and that might answer a lot of people's questions. So what happens if this fails? What happens if you are in a 1-key node whose siblings are all 1-key nodes? Well, you can't do a rotation. This is where we're going to steal a key from the parent. Now, since the parent was previously treated the same way as you were coming down the tree, the parent also will have at least 2 keys, unless it's the root, which we'll handle as our 3rd case. And so since the parent has 2 keys, you can always steal one and pull it down. So we know the parent has 2 keys because we treated it the same way. And so here's how we do the stealing. Suppose I'm walking down through a tree, and this is a portion of that tree, and I visit the 10. The 10 only has one sibling, and that sibling is a one-key sibling, so I can't steal the key from the sibling. What I can do is I can pull the 20 down. And this is just like the reverse of the operation we do in the insert. The 20 comes down, and then the 10 and the 30 are glued together around the 20. And this is sometimes called a fusion operation. Do you have a question over there? Okay. Are there questions about the fusion operation? All right, the third case is like the second case, except that your parent is the root and has only one key. And your sibling only contains one key. Well, then you still do a fusion operation, except now you're pulling down the entire root. And so you fuse yourself, the root node, and your sibling into one new root. And this is the case, and this is the only case where the depth of the tree decreases. Question about that? If the root has 3 children, then it can't have only one key. So you can always steal one from the parent, the root in that case. All right, so let's come back to our 2, 3, 4 tree here, and let's do a remove 40. Which is about as complicated as an operation as you can get on this kind of tree. It's going to exercise all our possibilities. Well, we start at the root, as always, and walk down the tree, and lo and behold, we have found the 40 right away. What do we do when we find the key we're looking for? Well, we replace it with the next higher key. And so that means we have to continue walking down the tree to find the next higher key. So what I'm going to do is I'm going to erase the 40 because that's the one I want to remove. I want to replace it with the next higher key, but first I have to find it. So let me just put in XX as a placeholder to remind me where the key is going to go when I find it. And now from here on in, I'm pretty much going to act as if I were doing a remove 42 operation, except that when I'm done, I'm going to put the 42 there. So I know I'm looking for the next higher key than 40, so I first go to the right, and I encounter a one-key node. So what do I do with it? I say, well, integration time. By rule 3, these 3 nodes are all getting combined into one node. And then I continue from there. I'm once again looking for the next higher key after the XX. And so I go down to this node called 43, and I say, okay, that's a one-key node. Got to handle it. Can I steal a key from a sibling? Well, not from 32, nope, but from 62, yes. So I do a rotation operation where the 62 goes up and the 50 comes down. And you'll notice that this node got transferred. This used to be a child of this node. Now it's a child of this node, because it's all the numbers between 50 and 62. And finally, I come down one last step, and I pay a visit to the 42. Once again, this is a one-key node. I can't delete this key until I have some other key in that node. So, can I steal a key from the sibling? Nope, there's only one key in the sibling. So it's time for a fusion operation. I take the 43 and I pull it down here. It goes in the middle here. This is now a single node underneath the 50. And finally, now because this node has more than one key, I can go ahead and delete the 42 from it without leaving it empty. And remember, the whole purpose was really to delete the 40. So now I can fill in my placeholder with the number 42. And that's my final 2, 3, 4 tree after the remove operation. Questions about that? So now we can talk about running times for all of this. But this is pretty easy because a 2, 3, 4 tree, well, it's not, if it has depth d, it's not too hard to show that it has something between 2 to the d and 4 to the d leaves. Basically, if all of the nodes are one-key nodes, it has 2 to the d leaves. If all of the nodes are three-key nodes, it has 4 to the d leaves. And so that makes the math really easy. The total number of nodes in the whole tree, let's call it n. We can show that even if in the smallest tree, where that only has 2 to the d leaves, if you add up all the levels, that has 2 to the power of d plus 1, big minus 1, or more nodes. And by taking the logarithm of both sides and turning them around, that means that d is in big O of log n. So the depth of the tree is always big O of log n. And, well, these operations that we do when we visit a node, these fusion and rotation and kick upstairs operations, are complicated, but they're not so complicated that they don't take constant time. Every time we visit a node, it only takes constant time to do whatever operation we have to do on that node and then move on. And therefore, the find, insert, and remove operations all have worst case times of the number of nodes you visit, which is the depth of the tree, which is log n. So it's easy to analyze. And compare with the binary search tree, worst case running time of theta n. So sometimes it's worth the extra effort. Any questions about that? All right, so there's one postscript I want to attach to all of these data structures so far, meaning hash tables, binary search trees, regular trees, 2, 3, 4 trees, binary heaps. Well, okay, not binary heaps, forget that. But for some of these data structures, you might want to deal with duplicate keys in a different way that prevents them from forming long chains in the hash table or long left of child relationships in a binary search tree, which is one thing you can do is just collect all of the entries that share a common key in one node. So in other words, each node's entry is now a list of entries. Now, this is especially useful in hash tables if you are expecting to have to store a lot of duplicate keys, because that way you can greatly reduce the length of your chain. Like now your hash table looks like this. Here's the top level array. Here's a chain. Maybe this is the key 3 and this is the key 7. And if there are a whole bunch of entries that all have the key 3, then you put those in a linked list here. And now the nice thing is, if I want to search for a key, the key 7, I don't have to walk through all of these 3 entries when I go down the chain searching for the 7. I can just go 3, 7. Oh, there's my target. So I don't pay for all the duplicates in the cost of doing a find operation in the hash table. So, any questions about that? All right, well, on Wednesday we will talk about graphs, data structures for graphs.